Good morning and welcome. Our list is nearly complete, but not quite. Okay, so it's good to just remember. We, of course, had the goal to get around the limit definition because it was tedious, it was annoying, it was difficult, there was nothing good about it. Uh, I guess the only good thing about it is the starting point and it can lead us to certain derivative properties that are true for if the function looks a certain way, and that allows us to get around looking at the detail of a limit definition, yet still find the derivative, which is ultimately what we are interested in. What is the derivative? What is the rate of change? What is the slope of the tangent line to a graph? I don't, however I can get there, the most efficient way is going to be the nicest. So we had our power rule as the first main property, that if I have x to the power of some number, then the derivative is always going to look like this. But I have other, I guess I'll call them supplementary properties that help me to isolate uh, things like x to the power of n. Like I have the sum or difference property. I'm just going to write property every time. These are all properties. Where if I have my function broken up into multiple terms, then luckily the derivative can be sort of deconstructed by looking at the derivative of the individual terms and then just putting them back in the same way they were sort of put together originally. So as simple as I might want it to be. Then I have a constant times a function property, where if I have some numbers floating around being multiplied to things with x's in them, or the variable, then I can just put those in front and focus on the essence of the function. That is a very, very nice property, that I can strip away all the fluff around the essence, where the variable is, and focus on that instead, in the process of trying to isolate something like x to the n, of course. Then I also have the situation where I could have the derivative of a constant. So the constant property, as I isolate the terms, strip away some stuff, I might just have the derivative of, it's not a number, it's the constant function. And because that is horizontal, the slope, of course, is 0, and it makes sense that the derivative should be 0 as well. Then we got into combining pieces of the function in different ways. One way is the product, so by way of multiplication, that if I have two pieces being multiplied together, then yes, I can look at those pieces in isolation, but it's not going to be quite as simple as the sum difference property would be. It is going to be the derivative of the first times the second, and I'm mixing notations here because I can and it's convenient, plus the first times the derivative of the second. So not terrible, but certainly not the simplest it could be. It really comes out of the proof using the limit definition, and it just is what it is. And there's not much I can do about it. Then you had to watch a video on the quotient rule, where the last way to combine functions in one of the four basic arithmetic ways is to have a fraction of functions. Then, let me just finish this one. Then the formula or the property just gets worse and worse and worse. It has a similar look to the product rule. The derivative of the top times the bottom. Now it's a minus the top times the derivative of the bottom. And then I'm creating another fraction, and it's over the bottom function squared. Again, it's not really a matter of personal preference. If I had my way, it wouldn't look like this. It comes out of the limit definition, and this is the way it is. There's no other way. I have a question here in Discord. When you use the product rule, what determines if it's a plus or a minus? The proof... Oh, I'm sorry. I am thinking of something else. I'm sorry. There is always a plus. Always a plus. I was channeling the sum difference property. The product rule has always a plus. The quotient rule always has a minus. So in the case of the quotient rule, it's especially important then to have the derivative of the top times the bottom be the first term. In the product rule, I can swap those around because I'm adding them. It doesn't really matter which one's first, which one's second. But in the case of the quotient rule, it does matter. There is a first one and a second one. Otherwise, my answer is not going to be the same. No, thank you for checking. I was thinking about something else. Not sure what. All right. So it's a good list. It's a good list, and we can do a fair bit. But we're always combining smaller functions to make bigger ones by way of really adding, subtracting, multiplying, or dividing. Then I have properties. I can totally handle all of those ways of making new functions. But there is one other way. There is one thing, and only one, and then we're done. One thing missing. There's another way to combine functions. There's one more. One more. So don't lose hope. Don't be discouraged. There is only one more. I'm not making it up. There will not be any other properties. There is one more way to combine a function. When I think about functions like the following example, let's call it, I don't really know what to call it. Let's call it y, it's fine. Root 2x plus 1. Now there is a square root in here. There's a square root function in here. And there's a 2x plus 1 also in there. They're combined, but not in an arithmetic way. It's not addition, subtraction, multiplication, division. It's none of those. It's a composition of functions. It's a composition of these two. What do we mean by composition? Now, informally, I say it's a function of a function. Now, I know for a fact, my bracket, stupid bracket, get away. No brackets there. I know for a fact that each and every one of you did this in your prerequisite courses somewhere. I know because I've taught those courses. It's really a question of, do I remember it, right? That is the pickle. So, in the interest of remembering, let's just take a moment, and by a moment I mean the whole rest of this class, to remember compositions of functions. Because if I don't, then none of what's coming up will make any sliver of sense. So, let's suppose I have an input. Let's call it x. Totally random name for an input, I know. And I'm going to do something to that input. I'm going to apply a function, and I'll call that function g. Okay, so this is I'm applying a function g, and then of course my output will be g of x, right? But now I'm going to take that answer and apply another function, and I'll call it f. So I'm now going to apply another function to the output I got after the first step. And therefore, my answer, my new input, is this g of x. So my output is f of g of x. You see how it's a function of another function. Is the function f applied to the function g, because it's sort of a sequence of functions, one and then the other. When I go directly from the input to this two-step end result, that's my composition. Composition of f with g. And for short, we want to represent that sometimes. There's nothing wrong with this. I actually like this. I prefer this f of g of x because it shows the sequence, what was happening. So it's great. But there's also one that you might recognize, a little circle notation. That I guess is the more official way of naming the composition of two functions. I'm going to try and avoid that because it's just not as nice as this guy. I prefer this guy. And it doesn't lose anything. It's a little more brackets, I guess, but not really. Okay. So this way is another way of combining functions that the previous arithmetic methods cannot reproduce. And again, if you have any questions, just interrupt me at any stage. Don't wait for me to ask, are there any questions, whatever. So we can get the above example, which was 2x plus 1 and then the square root, by saying this guy is going to be taking x to 2x plus 1, and this guy is then going to be, let's say just informally, we're going to get better in a second, the square root function, which takes whatever the input is and puts a square root around it. And in that way, I can nest functions inside of other functions and create composition of functions, or we just say functions of a function. Function of a function. Okay, we don't have to call them compositions. It's just a function of a function. Functions nested inside other functions. So our goal then is to just remember, because maybe some of us don't remember, and maybe some of us need the refresher. Maybe some of us are sitting there, it's perfect, I remember this like it was yesterday. Well then great. It's all the better. It's just going to get easier for you. No problem. But in the off chance that you need a little refresher, let's take our time. Because this last property very heavily relies on this. Very heavily. Okay, so let's just take some examples and make some compositions of functions. So let's take a function x cubed, the cube function. Let's take a function, well, for some reason I take 2x plus 1 again. Why not? Random functions. Then let's find f of g of x. It's a two-step process, right? I'm working inside out. So my inside function is applied first before I know what f is working with. I need to see what is inside there. So g happens first. It takes x to 2x plus 1. Then f is now applied to its input of 2x plus 1. Now don't get confused here. The x's used in the definition of my f function and the x's used in the definition of my g function are completely different things. They're not the same. And many people struggle with that. They think too hard, like this x and this x must be the same x. No, they're not the same x. They're general definitions. I could have called this a completely other symbol. I could have called it smiley face. And it takes smiley face and it calculates smiley face cubed. I could have used a completely other symbol. What shall we use? Maybe a star. And then it takes star, multiplies by 2, and adds 1. Because the exact symbol that we're using when we define a function is completely irrelevant. It's a temporary placeholder. People tend to recycle the x, understanding that that x doesn't mean the same thing from one line, from one definition to the next. So now when I have the input as 2x plus 1, what does f do to its input? It cubes it. So I will cube it. But of course, it's a prerequisite, and we spent some time with functions, but you may need to review. How do functions work? Functions of functions and stuff. This is all technically review. Let's just see what happens when I swap these around. Now f is the inside function. F is the inside function. G is the outside function. I work inside out. Which means f is happening first. It's taking x and it is cubing it. All right. Now g is ready. Its input is x cubed. What does g do? It multiplies the input by 2. It adds 1. Please notice that these are not the same. Now, in rare circumstances, they might be the same, but for most cases, they're just not the same, which tells me the order in which I compose these functions, the order in which I nest these functions inside each other matters a lot. It completely redefines the function. All right. Is this fairly familiar? Is it like you did it yesterday? Or is it like you did it 10 years ago, which means I don't remember a thing? That's up to you. But everything I'm doing, if I'm spending a day on this, then believe me, it is important. I will not waste an hour of your life if it wasn't important. And if you look at this and like, what on earth is happening? Maybe go visit Khan Academy or something, whatever resource you find useful, but don't think it'll just fix itself. It won't fix itself. So there's this direction, which is sort of the pre-calculus direction, where you're given functions and you have to compose them, build new functions, one inside the other. You just want to know which one. There are 2 examples here showing that I need to know which order I'm making a function of a function. This isn't really our goal. This was done. You've done it. It's over. Our goal is going to be given a function like this in the box. What were the original pieces so that when I make a function of a function, I get this function in the box? So our goal is going to be to deconstruct this composition, so to speak. Not that composing the functions isn't important, but it's not really what we need to focus on. Our focus will be to find the individual, let's say, whoops, I cannot write and speak at the same time. Individual functions used in the composition. So I'm given the final answer. Some functions were composed to give me this guy. What were the original functions? That is our question. And I want to make it very clear what our question is. It's not the pre-calculus exercise, it's backwards. But of course, in order for me to go backwards comfortably, I need to have done the forward direction many, many times and be super comfortable with it. So I will stress again, if you are not ready, go and review and do this right. Or I've seen it so many times, things fall apart when you least want them to. A month from now, and it's just going to be a complete disaster because some level in your foundation was not solid. Okay. I'm just going to do examples, and we'll do the problem book some other time. What did we have here? Let's pick something super similar. I'm going to write it like this for now. I'll give you how the functions were put together, f of g of x. And the end result is this. Let's start easy. There's no need. We have 25 minutes here. What were the original functions? So now I can think of an outside function and an inside function to help myself. Now I can't say for every single person that is listening to do the outside function first, to find the inside function first. It's a matter of personal preference. I kind of like to focus on the inside one first, but that's just me. It doesn't mean you have to. But very often it's a little bit easier to spot what is the inside function. The inside function in this case is going to be x squared plus 1. The brackets sort of give it away. And that's often the case, but not always. Once you have settled on your inside function, this is my choice. I think that this composition is built from two functions, and my inside function, I think, is x squared plus 2. What would you say is the outside function that then has to go with it to create my given function? What is the outside function? It is, let me get rid of my line here, x to the third. All right, good. And of course I can always test this, right? I can do my composition. Do I get the original back? Perfect, I do. I don't want to go too fast because people get confused. There's a lot of x's floating around here. There's x's everywhere. They all mean different things. When I define these functions, they're defined in isolation. And this x and this x, they're completely different x's. And that really bothers some people. Really bothers some people. Oh well, what are we going to do? Let us say I'm thinking of a function, and the end result is root 3x plus 1. Again, you decide, do I go outside first? Do I go inside first? Don't force it, whatever you spot. For me, personally, inside function, I spot it more easily, so I'll just go with it. The square root acts like a bracket, and that helps me spot, 3x plus 1. Once I have settled on my 3x plus 1 function, I'm kind of stuck. The outside function has to be the one that fits with it so that it gives me my end result, and it's the square root of x. Of course, I could have called this something else, right? I'm not married to the x in any way. We use x way too often anyway. I can call it squiggle, and then the square root of squiggle. What's that squiggle called? xi or something. It doesn't matter what the symbol is. It's irrelevant. Do whatever you want. It's just the function definition. All right. Don't worry. If you feel there are too many x's, change them. They're temporary placeholders. Who cares? I don't. And later on, we might actually change them and swap them out a little bit to make it as easy as possible. But technically, in books, they will just use the same letter because I guess they're lazy or I don't know, whatever the reason could be. I'm thinking of two functions. When I put them together in this function of a function way, I get 2x plus 1 cubed plus 2x plus 1 squared. What are the functions? Now, there could be a level of trial and error here, a little guess and check. That's okay. I think I see the same thing in the brackets. I'm going to try a 2x plus 1. That's okay. You can have a little guessing. The more you do it, the more experience you're going to have and the safer your guesses are going to be. Once I have settled on an inside function, what should the outside function be that has to go with it in order to produce my given function? X cubed plus x squared. Now, it wouldn't be this easy or even possible if the brackets weren't exactly the same, right? That allows me to do this. If I had an x plus 1, well, then I'm completely screwed. And I'm going to have to FOIL this out. It's just not a function of a function. But very often, the more complicated functions are built in this way from smaller functions. Yet, I don't have a way to handle the derivative, to find the derivative. I have no way. My current properties do not help me in any way with functions built like this. So we're on our way, and by tomorrow we'll find that property. But in order to understand that property, we need to do this. We need to be able to look at a function and identify, is this a function of a function? Yes or no? If yes, what are the pieces? Can I deconstruct it? Because I'm going to have to. I don't have a choice. That's going to be necessary in my property that we will explicitly state tomorrow. All right, new page time. What we're going to do is do the exact same function, but I'm not going to tell you what the names of the inside-outside functions are. Actually, this isn't the same function, is it? Oh, it is. 3x plus 1 square root. Yeah, same as the previous example. I'm just going to give you a function. It has a name. Its name is f. I don't know. I still recognize it as a function of a function. So that's the first step. You have to look at a function and recognize how I see pieces. How are those pieces combined? By way of this composition, which means I need to pull it apart. Inside function, outside function. But now I have the luxury of naming this however I want. I'm going to name it U. Why? Because that's what most books do. And if you happen to look at another book or something out there, chances are they'll use the letter U. I don't know why. I don't know why. They could use anything. U is the name of choice. I don't know why. It doesn't change what it is. It's still the inside function. Call it whatever you want. Call it G. I don't care what you call it. But it wasn't named for me, so I can call it whatever I want. I chose a U. Then I'm going to write the outside function as f of u. I'm going to use this u to help me write the outside function. It's not quite the same as what we did here. It's pretty much the same. This way of writing it in my opinion, is going to help me get the highest chance of success moving forward. Okay. So I specifically want to use my name for my inside function as the variable in the outside function, because then I can very easily see u is the thing inside the square root, u is equivalent to 3x plus 1, therefore I get the given function back. There's no doubt. I can see the composition happening here, I hope. Okay. So that's going to be my preference of splitting it up and writing it, because I want to help myself as much as possible. Again, it's personal preference, but I feel it works. I feel it works. I guess I have some experience, you might say. And in my experience, it was going to work. So now you can name this function whatever you want. I guess f is common, f for function. And I have something like that. Sometimes it's more obvious that I have a function of a function situation. Sometimes it's less obvious. Sometimes I have an option whether I want to see it as a function of a function or not. Let's suppose I want to see it as a function of a function. Now, what are my options? What could the inside function be? Well, let me just address the question. Why is u not shown in the original function? Because it's not going to look like this. They're not going to make it that easy for me, right? They're not going to come out and say, alarm, alarm, attention, this is a function of a function. They're not going to tell you that. They're going to hide it and say, here's a function. Do whatever you want with it. And it's my job to recognize that it's a function of a function. Or not. I don't know. They're not going to tell me it's a function of a function and name the inside function, which means if I want to see it as a function of a function, I have to name the inside function. And most books use a u. There's no need for me to go against that. The u works fine. So just for the sake of consistency, we're going to call it a u as well. So here I have, why am I doing this one? I don't want to do this one. This is silly. I have a typo here. Hold on. There we go. That makes way more sense. Because if it was just root x, I would make it x to the 1/2, and I have no issue, right? Function of a function is technically something that I just can't, my other properties don't work. I can't do much. I need something else. So this one works better. So I have outside function and inside function. And write this out if you want. For as long as you need to write outside, inside. Help yourself. Why not? But, okay, so one choice could be u being x plus 1, right? Going on what I've seen up here, the square root can sort of act as a bracket to highlight the inside function. Then certainly x plus 1 is going to be good. But once I do that, I'm sort of stuck. That the outside function has to be something that fits with my choice in order to create the given function. I can choose maybe an inside function, but once I do that, I'm stuck. And the outside function has to fit that choice. And the outside function, I hope we all agree, will be 5 times u plus, square root of u plus 1. So I'll emphasize here, this u was my choice. It's my choice. I could have chosen something else. Very often, there are other choices for the inside function. Not always, sometimes. More than you think. I could have chosen an inside function. I call it u. I could have chosen the square root of x plus 1. Why do I write so small? I don't know. Square root x plus 1. That's not any better. Then once I've made that choice, the outside function has to fit with it. And the outside function in that case has to be 5u plus 1. Which one's right and which one's wrong? They're all correct. This one's correct. This one's correct. Well, I can't think of anything else, but the good news here is that in this kind of question, where I have to deconstruct the given function into an inside function and an outside function, I've often have more than one answer. And they're all correct. They're both correct. Because if I compose them back, function inside another function, I get the original. They're both correct. Awesome. Great. That's good. More answers are correct. So it's kind of ironic. We tend to think of math as there is one right answer. It's right or it's wrong. There is no multiple answers could be correct. Well, in this case, there are multiple answers that are correct. And that's good news. I think that's great. That makes me feel better. I can write either one of these and I'll be right. Awesome. Let's see another one. 1 over square root of 5x squared plus 1. I claim for this one there are even more right answers, even more ways to split this up into an inside and an outside function. The problem is you have to see it. You have to first identify. This eventually has to scream at me, I'm a function of a function. Deconstruct me, please. So that's the first thing. And then the next thing is, okay, well, how do I want to do this? I'm going to write it in another way. Often we are going to write, because it's a choice, I'm going to say, okay, let's say u is 5x squared plus 1. That might be your first choice. Then my outside function has to fit that so that I get the given function, the original back. I don't have a choice. I can choose the inside function, which is an easier one to start with, I feel. Starting with the outside function, that never goes well. Once I've chosen one of them, for example, the inside function, the other one is set. I don't have any flexibility anymore. And the outside function would then be 1 over square root of u. But there are others. I can think of at least 2 others. There are more, but we don't have to get too fancy. There are at least 2 other obvious ones. Can you in the audience see another option for what I could have chosen u to be? There's too many u's floating around. It's confusing. My inside function is u, and I'm talking to you. Because if I see multiple options, it's going to make things better. I have flexibility. Flexibility is good. It's good. I can, remember I have to now, I understand in the chat it's different, but just while I'm thinking of it, I have to be very clear in how I write these things. Like, for example, in a test, you can't write 5u plus 1, right? It's not, first of all, I have to define u before I can use it. But I understand in the chat it's maybe clumsy to write exponents and all kinds of stuff. I could, I want a definition of u, which maybe you have the right idea, but what you wrote there, I haven't defined u. I need to define u in terms of x as my inside function. So we need to start with that. So maybe you want to update what you wrote? Maybe not. Can I see another choice for an inside function? I'm not saying you were wrong, I just didn't quite understand. The first thing I have to do is define x. I can't use, define u. I can't use it before it's defined. Square root of 5x squared plus 1. That's a different choice, but it would still work because then my outside function is 1 over u. Correct, correct. There are more. It's just getting better and better. You think, well, I don't need to write them all. I just need to find one. And if there are so many choices, my chances of finding one are better. So it's good news in that sense. I don't need to find them all. I just need to find one. I just want to show that there are many options. And they're all correct. It's good news. I think it's good news. What about just the 5x squared? Would that work? And if you say it works, what is the outside function? I know it's clumsy to write in the chat. You don't have to. I just want you to think about it. You don't have to say it in the chat if it's a little bit messy like this one would be. But it's important to just stop and think, if this was my inside function, is there an outside function for which it would work? I can't just choose any inside function, right? It has to be one that actually has a partner outside function that could give me the original back. Can't just randomly choose anything. But if I choose this one, it would still work. It would still work. Just giving a chance. Someone is typing. Don't want to cut them off and then it just takes time. 1 over square root of u plus 1. Also correct. I don't want it to sound like everything's going to be right, but many things can be the right answer. So now, it's good news and bad news. Yeah, good news. Oh, sure, I have many right answers. I could pick any one of these. Bad news is moving forward into tomorrow, some answers are going to be nicer to work with than others. Okay. These are all correct. The check marks don't change. But there are some better choices than others. Which one do I choose? As a general rule, to increase my chances of success, choose the one that has, no, I'll write it like this. The one that has the easiest derivative for the outside function. Now, of course, I'm limited in my time. I can't show why I'm saying this. Tomorrow we'll see. I have many choices here. I honestly do not care how complicated the inside function is. I can't tell you how little I care about that. I care about the outside function being the simplest, the easiest to find the derivative. So of these, I will not choose the last one. I'll put a sad face next to it. It's still correct, but moving forward, when I'm putting a derivative layer on top of this, that guy is not going to be the nicest outside function to work with. I don't even know what to do. at this stage. Whereas the first two are going to be pretty doable, right? This one I can see as u to the negative 1/2, so it's a simple power rule. Smiley face, happy face. This one is marginally easier. It's u to the negative 1, but in terms of the derivative properties to use, it's still just a power rule. It didn't really get actually easier. I didn't save the number of properties that I had to use. It's still the power rule. A u to the negative 1/2 and the u to the negative 1 in terms of using the derivative properties, it's exactly the same. So it wasn't really easier. But both these first two would have been better choices moving forward. Again, at this stage, they are all good. But this is half of the picture. The other half, we of course have to do tomorrow, where I actually find the derivative. Then it turns out, even though these are all correct, some are going to be a little easier to work with than others. Which ones? The ones that have the outside function the easiest to find derivative. The easiest to find derivative. Okay. You'll just have to take my word for it now, because we have part 2 coming tomorrow. So the first thing to do, you can look at problem 6.1. Don't do the problem, because we haven't said what the chain rule is, but you can use those functions. They're all functions of functions, all compositions. Can I deconstruct them? Do I have choices? What do those choices look like? That is the first step. Before I put the derivative layer on top, I need to be able to deconstruct this. And I need to be able to see my choices. These are, for example, 3 obvious choices that come to mind first. I need to know what my choices are so I can pick the most convenient one moving forward. If I just write down this one, this last one, and not think about my choices, not think about other choices that I could have had, and I want to move forward with that one, my life could be way worse than if I chose the first or second option. So I need to be able to see my options and be comfortable in deconstructing this into an inside and an outside function. Then from those, whether you write them out or you just see your options, pick one that is going to be convenient moving forward. And for that, I use the outside function and ask myself, how easy is it to find the derivative of this guy? Yeah, it's a power rule. Pretty straightforward. So that's a good choice. How easy is it to find the derivative of this middle one? Yeah, power rule. Pretty easy. Good choice. How easy is it to find the derivative of that last guy? Bad choice. There will always be a good choice, but you need to know your choices and then pick the right one. So, unfortunately, we have to pause it there. Don't have a choice. We ran out of time. And then once you're comfortable with that, tomorrow I will assume that you are, and we can put the derivative property layer on top of this. And if I build this correctly, there is no reason for this to be overly complicated or confusing, but it needs to be built up in the right way. Because on the surface, at the face of it, it looks complicated. And it certainly is the most complicated of all the properties, which is why it's last. But if I know my path through this question, when I look at the function of a function, there's no significant challenge to it. It's like anything else. I just need to know how to look at it.